greatest integer function basically. So we have seen greatest integer function, its definition and few examples. Now we will discuss Legendres theorem. Before that, we should know a definition of factorial. What is factorial? Say n factorial. N factorial is defined as product of first n natural numbers. N factorial is defined as product of first n natural numbers. Let's say for example, 5 factorial. 5 factorial. This will be 1 into 2 into 3 into 4 into 5 equivalent to 120. So this is what n factorial is. Some important observation are n factorial equals to n into n minus 1 factorial. Now we know that n factorial is defined for natural numbers, product of first n natural numbers. Sometimes while solving few problems in combinatorics, say, just I am giving a hint, in combinatorics there is a very special thing, choosing say NCR, also denoted in this way. We will see what is this symbol and other thing. I'm just giving you a hint for those who know what is the meaning of NCR. We will see this in combinatorics. NR, it's also denoted in this way. These are brackets. This is simply n factorial over r factorial into n minus r factorial. This is the definition of NCR. Definition is different. This is the mathematical meaning, I can say. Suppose in this case we have 5 choose 5. Suppose we have 5 choose 5. Now what will be the value of 5 choose 5? This will be simply 5 factorial over 5 factorial into 0 factorial. Conventionally, this value n choose n, there is a significance, theoretical significance of n choose n. This is 1. What does this n choose n means? N choose n means in how many ways. Say for example, we are having 3 things A, B, C, and we want to choose 2 things. 2 things. So n choose r means in how many ways we can choose 2 things out of these 3 things. In how many ways we can choose? We can choose AB, BC, CA. So 3 ways we are having. And basically if we see the value of 3 choose 2, this is 3 factorial over 2 factorial into 1 factorial, 1 factorial, this is equals to 3 only. So we are having n number of things and we are choosing 2. We are having n number of things, 3 things, and we are choosing 2 things. In how many ways we can do this? We can do this in 3 ways. That is the meaning of n choose n. N choose r. Now we are having 5 things. Say we are having 5 things or 3 things only. A, B, C, 3 things, and we want to choose all of the 3. In how many ways we can do this? Only one way. That we choose all of them. Only one way. So 3 choose 3 equals to 1. So 5 choose 5 will also be equals to 1. These things we will see in detail in combinatorics. Here we do not need that much detail. Now simply these and these are cancelled, 5 factorial, 5 factorial, which implies that 0 factorial equals to 1. This was only one such proof of 0 factorial equals to 1. Lot of other different ways are there to prove that 0 factorial equals to 1. 3-4 ways are there. But basically factorial is defined for natural number. Even for negative numbers also this is not defined. Only 0 factorial is a special case where 0 factorial equals to 1, and basically it's defined for natural numbers. So these are few properties of n factorial. Now suppose we have been given 5 factorial and we are asked that 5 factorial can be expressed in some 2 to the power n into some lambda, where lambda belongs to integer. This z here denotes set of integers. Set of integers. Z denotes set of integers. So 5 factorial can be expressed as this 2 to the power n into this lambda, and we want to find the exponent of 2. We can say exponent of 2 or maximum value of this n, when n also belongs to integer definitely. How we can find? For this we use Legendres theorem. Let's read what is this Legendres theorem. In the prime factorization of the product of n equals to, as I said, n is the product of first n natural numbers. The index of prime factor p, index means exponent. Say for example, in prime factorization of the number 4 factorial, which is equals to 24, is simply 3 into 8, that is 3 to the power 1 into 2 to the power 3. By the word index, we mean this exponent or whatever, indices. So this we can find with the help of Legendres theorem. In the prime factorization of the product n factorial 1, 2, 3, n, the index of prime factor p is given by this expression. What these boxes? These boxes denotes greatest integer function, and that is why we are studying this factorial in greatest integer function. You can just see that it is continued, so on. Okay, so on. Now a case will be there when, okay, I'll just show you example, then it will be more clear, I guess. So using this formula, let's try to find out the exponent of 2 or the indices of 2 in 5 factorial. This will be simply 5 divided by 2 plus 5 divided by 2 square plus 5 divided by 2 to the power 8. Now I know that we do not need to write this part. Why? Let's see. 5 divided by 2 is what? 2. And 5 divided by 2 square means 5 divided by 4, and we are getting the greatest integer function. This will be 1, and this will be what? 0. Because, sorry, this will be 2 to the power 3, which is equals to 8, and 5 by 8 is less than 1. So box of, we have seen that box of our greatest integer function of 0.3 this example I have used equals to 0. So this will be also 0 plus 0, and after this all the terms will be 0 only. All the terms will be 0. So the indices of 2 is simply 3. In this way we can solve a lot of different kind of problem. Just remember that when we are applying this formula, right, Legendres formula and factorial, this number p has been specially denoted. P belongs to prime natural numbers. P belongs to prime natural numbers. This was quite easy. Now let's solve 2-3 problems based on this Legendres theorem. Then we will move to our discussion of assignments or practice session, whatever. Find the maximum value of k. Here k belongs to natural number. K belongs to natural number. Oh, sorry, k belongs to integer. This lambda belongs to integers. So this is also very simple thing. We have already did this for, we already have solved this for 5 factorial. Similarly we can solve, and this 11 is also a prime, so this will be very easy for us. This will be simply 1986 by 11 plus 1986 by 11 square plus 1986 by 11 cube, and for 11 to the power 4 this will be more than 10,000. So 1986 by some divided by some number where denominator is more than 10,000 is useless. We need to find this expression's value. Just calculate the value. I can only give you the answer. Answer is 197. This calculation is your part. Now let's try to solve similar kind of problem for a number which is not prime. For a number which is not prime. This question. This is what is written now. Find the number of zeros. Find the number of zeros consecutively from the right side in 201 factorial. Very simple question. What do I mean by consecutively from the right side? Just say for example, I can't move further right. Just say for example we are having a number 2010 2000. How many zeros are there consecutively from the right side? 3 zeros, and this can simply be written as 20102 into 1000, that is 20102 into 10 to the power 3. So here in this problem in 201 factorial, we want to find the highest indices of 10. We want to find the highest indices of 10. And remember, 10 is not a prime number. 10 is not a prime number. 10 is not a prime number. So we cannot directly apply, we can't directly apply this Legendres formula here. So how we will find the value of this 10 to the power n? Simply prime factorizing 10, we have 2 to the power n into 5 to the power n. We can find out the value of indices of 2 as well as 5, and then we will multiply them to get the answer. Let me solve. I guess most of you have already solved this. 201. First let us find the indices of 2. We are finding the indices of 2. Okay, first step, by 2 plus 201 by 2 square plus 201 by 2 cube plus 201 by 2 to the power 4, so on. This will continue. Let me directly write 201, this will be 100 by this will be 50, this will be then 25 by 2, 12, this is so on. Okay, this is continued. I am just directly writing mental calculations. Okay, 3 1, and after this will be 0. We will add them up, 100 150 175 175 plus 175. Up to this we are having 175 plus 12 plus 16 18 plus 7 sorry 4 175 whatever 22 177 197. I guess if there is some calculation problem, then you can easily sort it out. So 197. Now let us find out the indices of 5. Indices of 5. (201 by 5), 201 by 25, that is 5 square, plus 201 by 125. After this, whatever will be, that will be 0. Common sense. 5 divided by 201, 20, 40, 8. This will be 1. This is 49. This is 8. And now 1 is 197, indices of 2. Another is 49. What will be the indices of 10? 2 to the power 197 into 5 to the power 49. What will be the indices of 10? Let us take 2 to the power 47 common. Okay, 49. 49 into 5 to the power 49 multiplied by some 2 to the power lambda, whatever be the lambda. What is lambda? Lambda is this, lambda is 197 minus 49. Please do the calculation. Okay, I'm just considering this some lambda. This will be 10 to the power 49. 2 to the power lambda. So number of zeros consecutively from the right side are 49. Now one simple calculation hack is that the indices of 5, one is 5 to the power a, another is 2 to the power b. The indices of 5 or any prime number which is greater will always be smaller, that is a will always be smaller than b. So while in such kind of factorization, finding the 10, we can just find out the value of 5, indices of 5, and definitely this will be greater than whatever value of 5 we are getting. So we can say that 49 will be the answer, because in this case also indices of 5 was 49. So we do not need to calculate this part. Just find out 5. Definitely this will be greater than whatever indices of 5 we are getting, and we can put it. Say for example, we have been asked to find out the indices of a number 36. 30, which can be written as 2 into 3 into 5. So here clearly indices of 2 will be greater than indices of 3, and indices of 3 will be greater than indices of 5. So if we just find out indices of 5, we can say the indices of 30. Indices of 30 will just match with this 5. Now another case, the case of into 2. 60. 2 square into 3 into 5. Here in this case, we cannot apply this calculation hack. Why? Because here the power of 2 is something different in each prime factorization. So here if we apply this calculative hack, then our answer, whatever we will get, will be wrong. These are some simple things that we need to understand. Last question from Legendres theorem. Find the maximum value of n. I'm reading it out. Find the maximum value of n. N belongs to natural number. Q belongs to natural number. This is Q, not theta. Q equals to this is 1001, 1002, 1003, so on. 2023 divided by 13 to the power k. This is damn easy question. Easier than what we have did in 30. Just solve it. I'll just give you a hint. 1001. So if I am writing here 1000 factorial into 1001 into 1002, so on, 2023. One thousand factorial and divided by 1000 factorial. into 13k. So this will be simply 2023 factorial divided by 1000 factorial into 13k. We can find the exponent of 13k in this expression. In this expression, we can find out the exponent of 13k and exponent of 13k in this expression. Say, here the expression of 13k, I am saying say, here the expression of 13k is 13 to the power 100, and here the indices of 13k is 13 to the power 50. Then the maximum value of k possible is what? 100 minus 50 to k. I am saying that say, because I am not calculating this part. Calculation is yours. This is not mine. So this was all about Legendres theorem. You can take a snap of the proof if you want. Proof is not important for intermediate Olympiad level, but if you are moving for something higher than this, then okay, we can go for proof. Now let's move to another thing, that simply here also proof is not required. I would say simply you just remember this, write in your copy. Till now for intermediate Olympiads, I haven't find any great application of this Hermite's identity. Just you can write this Hermite's identity. Box x plus 1 over n, like this. Now let's move on to problems. Assignment has been attached here. We're not going to solve all the questions. Basically, these two questions are similar questions, this question and this question. So we'll just solve one question. Just I will give you a hint for one question. Another question will be easy for us. Find the real solution of 4x square minus 40 box x plus 51. How we are solving this question? Simple mathematical iteration are enough to solve any question, whatever be the question of whatever difficulty let it be. Question number 3. What was the question? 4x square minus 40 box x plus 51, right? How we will solve this question? Actually, this is a very easy question. There is nothing much difficult. First, one thing that we have noted is x is greater than box X in the definition. So for basic inequalities that we have covered, I guess, or we all know this. Say for example 3 is greater than 2, then minus 3 will be less than minus 2. Minus 3 is less than minus 2, and vice versa is also true. Minus 1 greater than minus 2. Now multiply both the sides by minus, inequality signs will be changed. Vice versa is also true. So this is what we are covering in basic inequality, that the inequality side gets changed. Here we can see inequality sides gets changed when multiplied by something negative. And this expression x square is also greater than 0 and 51 is also greater than 0. So we are simply adding them in both the side, and adding a positive expression in both the side doesn't affect the symbol. Even adding something negative also doesn't affect the symbol. Adding something negative or positive doesn't affect the symbol. Now we just simply need to, what is happening this again and again, I do not understand why this happens. Okay, this is 51. We simply need to factorize this expression. I guess I have written something wrong. Oh yes, there is 40. Multiply this equation. Multiplying a equation with a number greater than 1 doesn't affect the symbol, doesn't affect the sign of inequality. This will be 40. And here also this will be 40. 40, 40. This will be 40. This will be 40. Now we need to factorize this side. What are the roots basically? 4x square minus 40. X equals to minus b plus minus root over of 1600 minus 4ac, 16 into 51 by 2a, that is 8. Quadratic formula, we all know this. Minus b, 40 plus minus 40 plus minus 16 was common in both the sides. 16 was common. Root over of, let us take 16 common, this will be 100 minus 51. Oh, that's easy factorization. That's easy factorization, not a difficult one. This will be simply minus b plus minus 4 into 7 over 8. 4 into 7 over 8. Say whatever be the roots doesn't matters. I'm just removing everything because there is a possibility of mistake in such large calculations. I'm just assuming here. Here also I'm not calculating. Say the roots be 4 and 8. Then the roots of this equation lies in this interval. Roots of this equation lies in this interval 4 and 8. Can be equal. I guess that my calculation wasn't wrong here, so I'm writing the original roots. The roots of this expression are 3 by 2, 17 by 2, which implies that the roots of this expression, right, whatever be the root, let it be anything, doesn't matter, lies in this region, that is between 3 by 2 or 17 by 2, which implies that box x okay, not box x, this is x less than equals to 17 by 2 greater than equals to 3 by 2, which means that box of x, take the greatest integer value on both the sides, this is something 8.5, this will be 8, this is 1. Now the calculations are really easy. How? Just we need to consider 8 cases. First case I am showing, let box x equals to 1, and we will solve this 4x square minus 40x plus 51. Four x square minus 40 into 1 plus 51 equals to 0. We will get some value of x after solving, say k. We will get some value of x, say k, plus minus of k, or whatever be the value, not plus minus k. We will consider the positive value. Now there we need to find out that whether box of k is equals to 1 or not. If box of k equals to 1, then x equals to k is a root of the given problem, and if it doesn't equals to 1, because this is the case, we are solving the case for box x equals to 1. If it doesn't equals 1, then k is not a root of the equation. So this case, box x equals to 1 will not be possible. In this way, we need to find out the case for box x equals to 1, 2, 3, so on up to 8. And we need to check whatever value of x we are getting. Here we got k, that whether the box of k matches the value or not. This is the way of solving this kind of problem. Was asked in PRMO 2012. Canada and some other contest also. This kind of problem we have already solved. Another chosen problem is this. A problem involving root. This is very easy. Just find the first few terms, you will get a pattern. For root 1, this will be 1. For the next few terms. For root 2, this will be 1. For root 3, this will be 1. From root 4, this will be 1. For root 5, this will be 2. For root 6, this will be 2. For root 7, this will be 2. Box will be 2. For root 8, also this will be 2. For root 9, box, this will be 3. How many terms we are getting? 4 terms. Right, 4 terms. Here we are getting 3 terms. 2, 3, 4, 5, 2, 4, 5, 6, 7, 8. Yes. 1, 2, 3, 4, 5. 5 terms we are getting. In this way, we will get odd number of terms. 1 into 3 plus 2 into 5. So on, we need to find out a pattern. Writing the first few terms. This is easy. This question. Finished one question. Okay. We have already provided these questions in the form of assignments. So we're not giving enough time to just look at the question and waste the time. Now this question is a kind of some critical Olympiads question based on simple things, very simple thing. Just simply see some facts here. It is following a certain pattern. 201 into, see this, 201 into 1 into 2020, not up to 2021. What might be the reason? The reason is very simple. This 1 plus 2020 equals to 2021. Similarly, here is 2 and the term here is 2019. Before this term 2019. So this 2 plus 2019 is again 2021. So this is one pattern. Now let's work on this pattern. 201 into 1 over 2021 plus 201 into 2020 over 2021 equals to 201, right? Equals to 201. Just take 201 common, we'll get 2021 by 2021. But this expression does not belongs to any integer, as well as this expression does not belongs to any integer, but their value is integral. Interesting, right? That is, simply speaking, x and y are not integer, but x plus y belongs to integer. X comma y does not belongs to integer, which means what? Say x can be written as integral part of x plus fractional part of x. Similarly, y can be written as integral part of y plus fractional part of y. Now the fractional part when added should be integer. Because fractional part exists. X and y individually doesn't belongs to integer, means these parts are non-zero. These fractional parts are non-zero. But when these fractional parts are added, they are becoming some integer. And what is the possible integer? The possible integer is none other than 1. And there we have solved the entire problem. Say for example 2.3 plus 3.7. This number neither belongs to integer and this number also neither belongs to integer. But 0.3, which is the fractional part of this part, and 0.7 add up to 1, and this is an integer, and hence their sum, which is 6, belongs to integer. This is the formulation. This is the main manipulation, not formulation, whatever be the English word. Which implies that if we add this x plus y, they are integral, fine. Box x plus box y, and this sum we have proved. Is 1 plus 1, right? This was a nice question. Which means that box x plus box y equals to x plus y minus 1. Now in this case, what is x plus y? X plus y is 201. And for all the cases when we are taking pair of two such number, let me give you another example. 201 by 2021 into 2 plus 201 into 2019 plus 2021 is equal to also 201. So all these number add up to 201. So their integral parts value will be what? X plus y minus 1, that is 201 minus 1, which is equals to 200. Now we just need to calculate how many number of terms are there. How many pairs we can form. And our problem is over. How many pairs we can form? If there are say 10 numbers, how many pairs we can form? We can form 5 pairs, and now there are 20 numbers. So the number of pairs 20 by 2 into the sum whatever we are getting. This will be sum 20. This is the value of S. This is the value of S. This was quite easy problem. Again, again a problem that we are going to solve is this. Why not this? Because both are same problem only. This was asked in some 90s. The year is not written here, I do not know why. Basically, these and these questions, those who have read the questions, those who know, these are same problem. These questions were given in assignments. All these questions. And these assignments are available in Google Classroom. Link given in description. Box x whole square equals to curly x plus x. Then we have a last question from Putnam also. So this beautiful question based on the idea of, it's not based on the idea of any kind of geometric progression. Basically, the same question was asked in Canada Mathematical Olympiad. I haven't mentioned the year. And the same question was asked in PRMO 2007. So let's see. Just one of these two questions we'll see. Okay, let's discuss this Canada's question. So what is given in the question is very easy. Box x squared equals to curly x into x. Now, whenever we see this curly x, the first thing struck in my mind is that this curly x lies between the first thing which comes in my mind when I see this curly x is curly x lies between 0 to 1. Now we will use this simple idea to solve the question. We know that this belongs to natural number, not natural number, integers. Say that box x equals to some n, where n belongs to integer, and say for example some n we have p, some p equals to this curly x. This is just a substitution for, this will help us to write, because always writing this box is quite exhausting task. So what will be x? X will be n plus p, because we know that x equals to box x plus curly x. Quite simple. From this we have n square equals to n plus t into t, p, n plus p into p, where p is less than 1, greater than equals to 0. So n square is greater than 0. We know that anything square is greater than 0, greater than equals to 0, which implies that n plus p into p is also greater than equals to 0. Now this part is also, we know that is greater than equals to 0. P is greater than equals to 0, we can see p greater than equals to 0. So we can write n plus p greater than equals to 0. And n belongs to what? Integers. N belongs to integers. So we can say that n is also greater than equals to 0. Now why n is greater than 0? How we are deducing this? This is quite simple. What is p? P is some fractional number. I'm just showing you an example, say 0.9 also. And n is what? Some integer, right? So some integer plus 0.9 is greater than 0. If this integer, what are the possible values of this integer? Say 0, then this is satisfying. Say -1, -1 plus 0.9 is not greater than equals to 0. If I write greater than equals to 0, then this is wrong. So the least value after 0 is -1. For -1 it is not satisfying. That means for any other negative integer this will not satisfy, which implies that this n is greater than equals to 0. Quite simple. Always take such examples if you are having difficulty in understanding. So these are the few things we are having with us, which would give us an idea about the problem. N is greater than equals to 0. P is also greater than equal. So now we are having these identities in our hand. Another simple iteration. 1 into n plus 1. Okay, 1 into n plus 1. And this 1 is greater than p. 1 is greater than p. P greater than equals to 0, which implies that this is greater than p into n plus p, right? Another important iteration, which implies that n plus 1 is greater than n square. We got the required result, right? That is n square minus n minus 1 less than 0. N belongs to integer. Now applying the most popular wavy curve, I'm just giving you the approximate roots. Find out the roots and apply wavy curve. The roots are approximately minus 0.618 and 1.618. Now n belongs to integer. What are the integral points in this region? This is 0 and 1. So n equals to 0, 1. Now we need to find out the value of, because we need to find the value of x, right? We need to find the value of x for any equation. We need to find the value of x. So let's find out x. We got n equals to 0, 1. So if n equals to 0, then 0 square equals to p into 0 plus p, which implies that p equals to 0. So this implies that x what is happening? Which is equals to n plus p is equal to 0. Now another value of p is also there. Just put n equals to 1. We have 1 equals to p into p plus 1. Solve this, you will get some p. Let the value of p that you will get after solving this equation is k. Remember that this is a quadratic equation, right? This is a quadratic equation. So you will get two values. Solving this quadratic equation, we will get two values of p. One is positive. Among the two values, I guess only one value will lie in the region 1 less than 0. and the equation which will satisfy this inequality will be our, and the value of p that will satisfy this inequality will be the exact value of k. Let me solve it. Let me solve it. Okay, so the value of p will be minus 1 plus root 5 by 2. This is greater than 0. What is the method to check? Simple thing. Root 5 is some 2 point something, or you can also check in another way is also there. 5 square greater than 1 square, sorry, 5 is greater than 1 implies that root 5 greater than root 1, root 5 minus 1 greater than 0. So this is greater than 0 and less than 1. Less than 1. Less than 1. So this is the value of p which we will select, and hence the value of x for this case will be equals to 1 plus minus 1 plus root 5 by 2, which is equals to 1 plus root 5 by 2. So there are two values of x, and this is our answer. Quite a simple problem. Okay, I guess there was a homework question. Actually, we think that this log is not required for so-called PRMO. Log is not required. That's why this question is homework question. Basically, it's a easy question. It's a easy question. Those who do not know log, they needn't worry, because this is not relevant for PRMO. Simple thing, right? Now let's move on to a good question. Find the number of positive integer x. What is written in the question? Let me write. Let me dictate. Find the number of positive integers x which satisfy the condition. The condition is box x over 99 is equal to x over 101 box. We need to find the number of positive integer x which satisfies this condition. Was asked in RMO 2001. Is based, actually it's this question is not based. This question in PRMO 2012, we can say, was based on this RMO question. So for this part, we have shown a lot of similar questions. This is a damn easy question, just based on some little iterations. Okay, let me solve this. How may we solve this question? This is basically again a question based on simple kind of this question. Okay, not this one. Not look at this question. Please do not have a look at this question. Please just ignore this question. This is our target. This is our target question. Maybe you have seen this question a lot of time. Still, this is an important question. So say this is equals to 0. For how many numbers this will be equal to 0? For x less than 98. Now why x less than 98 when x equals to 99? This will be 1 and this will be 0, and 1 is not equals to 0. This will contradict at x equals to 99. At x equals to 99, this will be 0, this will be 1, and 1 is not equals to 0. So 99 is not possible. 98 is possible. 98. This is for the first case. Now say this is equals to 1. For how many number this will be equals to 1? For x equals to 101, this part will also be equal to 1 and this part will also be equal to 1. Now what will be the upper limit for this? The upper limit for this, upper limit will be 99 into 2, 198, 197, because for x equals to 198, what will happen? This will be 2 and this will be 1. Again 2 not equals to 1. So how many number of values we are getting? Okay, this was for x equals to 1. Let me write another case for understanding purpose. Equals to 2. Then what will be the starting value or the lower limit? I can say 202. And what will be the upper limit? This will be 2 into 99 minus 1, right? This will be the upper limit. Not 2, this will be 3. This will be 3. This will be the upper limit, because for 3 into 99 divided by 99 box will be 3. That means this part value will be 3. So before that number, before this number, the value will be 2 only. The value of this box will be 2. And that is the logic behind solving this problem. And what can we conclude about the lower limit? This lower limit, this is nothing else but simply, if this is k, if this is k, this is 101 into k, and the upper limit is k plus 1 into 99 minus 1. So how many solutions are there in between them? Okay, suppose we are given number 23 up to 31. How many numbers are there? Including both are included. How many numbers are between them, including 23 and 31? This is written as 31 minus 23 plus 1. So how many numbers are there in this set? In this set, how many numbers are there in this set? This will be given by k plus 1 into 99 minus 1 minus 101 into k plus 1, which is equals to 99 minus 2k. These are the number of solution. So number of solution for box x over 99 into x over 101 is equal to k. Number of solutions satisfying this are 99 minus 2k. Now a time will come when this value of k will be so large, that this will become a empty set, empty set, empty set, a null set. When this condition will happen, clearly this 99 minus 2k will be less than equals to 0 when k equals to 49. Sorry, not 49, when k equals to, k is greater than equals to, this will be less than 0. That means the number of element in the set will be less than 0 when k, solve this inequality, quite simple, k is less than equals to 49. So what is the maximum value of k? Maximum value of k is 49. Maximum value of k is 49. So how many integers are satisfying this? How many integers are satisfying this? For 0, how many integers are there? What was actually asked? Find the number of positive integers. Okay, 0 is not a positive integer. 1 to 98. There are just a simple thing, that for this case x equals to 99 over x equals to 101 is equal to 0. It's satisfied by 98 positive numbers. Why? Because we cannot include 0 in this case. Okay, x equals to 0 is not possible because the condition given is for positive numbers. So there are 99 cases, 98 cases, sorry, 98 cases. So the numbers satisfying this are 98 plus sigma k equals to 1 up to 49, 99 minus 2k, which is simply arithmetic progression. Solve this, the answer is 2499. I'm giving the answer for this question yet, and for the last question I'll not give you the answer. Determine the number of real solutions of, determine the number of real solutions of this, what is this, x by 2, box x by 2, box 2x by 3 is equal to x. Let's solve this. This question is yet another beautiful question from number theory. Yet another beautiful question from number 3. There are different kind of approaches, but here, since this, what am I doing? Denominators are quite small number. We can apply a very popular remainder theorem. Now, how to apply remainder theorem? We'll just assume x is equals to some 6q plus r. Why 6q plus r? Because LCM of 2 and 3 is 6. That's why 6q plus r. According to remainder theorem, this q belongs to integer. And r is less than equals to 5 and greater than equals to 0. These are the possible values of r. Remainder theorem is quite basic, and this is even the basic remainder theorem. R also belongs to integer, because we need to find integral solutions, right? And this is quite a small number, so we can apply this remainder theorem. This will give us 6 cases. Why 6 cases? Because there are 6 cases, right? So solving 6 cases are quite easy for us. Let's solve. Putting x 6q plus r over 2. (12q plus 2r over 3 equals to 6q plus r. Let me just see, am I correct or wrong? Yes, I'm correct. Three q r by 2 plus 4q two r by 3 6q plus r. Cancel them. We are left with q plus r by 2 plus 2r by 3 equals to r. Which implies that q equals to r minus r by 2 minus 2r by 3. If I am not wrong, then this should be correct. Now remember that this q belongs to integer, so this part also belongs to integer. Now how do we evaluate this part? Right, we can easily evaluate by putting the values of r. What are the values of r? R equals to 0, 1, 2, 3, 4, 5 by remainder theorem. Just put 0. You will get q equals to 0. and q equals to 0 is definitely integer, but what was given in the question, I need to check. Determine the number of real solutions. So they said number of real solutions, right? Real solutions. So anything belongs to integer will satisfy this. Anything belongs to integer will satisfy this. Just only one criteria in this question, that q belongs to integer, so this part also needs to belongs to integer. Q equals to 0 is satisfying. For r equals to 0, r equals to 0 gone. Now let's check r equals to 1. For r equals to 1 we will have 1 minus 0 minus 0 equals to 1. For r equals to 1 is also it's satisfying. Similarly, check for r equals to 2, r equals to 3. Let's check for r equals to 2. The last thing I'll check. For r equals to 2, let me check. For r equals to 2, let us check. 2 minus r by 2. 2 by 2 minus 2r by 3. Just a minute. Actually, all the values from r equals to 0 to 5 should satisfy this, but this will definitely not ask the number of real solution, right? This will definitely not give us the number of real solutions, because here we will only get the integral solutions. Here we will only get the integral solutions, right? Not the real solutions, because real solutions, there might be some fractional numbers which satisfies this. There might be some fractional number which satisfy this. So the question should be, let me edit the question better. The concept was for integers values. The concept, so this is now our question, because we are editing the question. Determine the number of integral solutions, because for generally for this box kind of questions we solve it for integers. So this was the technique by applying remainder theorem. This question was not just for problem solving, this was just for showing you the techniques of solving problems, how we can apply remainder theorem, go for the LCM and then apply remainder theorem, how we can use observation and find out the values in this RMO question, how we are applying this inequality, and the last question based on Putnam is really excellent question. This will use a simple binomial identity, simple common binomial identity. Last question. Let's start. 10 to the power 20,000, 10 to the power 100 plus 3. Ten to the power 20,000, 10 to the power 100 plus 3 box. So let's assume that n equals to 10 to the power 100. My handwriting is really ugly, that's why I'm writing that big letters. N to the power 200 over n to the power nothing, n to the power nothing plus 3. Very easy. Let us use this n plus 3 format to solve this question. Just a minute. I'm too confused for this question. Really, I'm confused. n plus 3, right? How this would be? N to the power 200 is neither odd that I can apply something for odd numbers. Let me just check. That's why it's Putnam question. Okay, right. It needs to be beautiful, elegant, and difficult. Let me write minus only. I've got an idea. Minus 3 to the power 200 n plus 3 plus 3 to the power 200 over n plus 3. Now let us just apply a simple logic. What is n? N is 10 to the power 100. And what is 3 to the power 200? 3 to the power 200 can be thought of as 9 to the power 100, right? 3 to the power 200 can be thought of as 9 to the power 100. Now n is definitely greater than 3 to the power 200. So the box of this part will be 0. Let us take it outside. Before taking it outside, we need to prove that this is integer. Then only we can apply. How we can apply? Which formula we can apply? We'll show this. Just wait. Let us work on this part separately. N to the power 200, right? Got it? Now there is a very special identity for this a n to the power. Sorry. For this a to the power n minus b to the power n. Very special identity. It's something like a minus b into a to the power n minus 1. Then I have forgot. Actually, then I didn't remember this identity. I just remember that this is some a minus b into some k. Okay, I just remember this. Let me just evaluate. For a cube minus b cube, this is a minus b into a square plus ab plus b square. Okay, got it. So the ID or identity for this will be a to the power n minus 1. I'm not pretty sure, just check this identity. A to the power n minus 2 into b plus so on. This is n minus 2, right? So on. This one, right? So on plus b to the power n minus 1. This is a famous binomial identity. If I have written anything wrong, then I do not know, but this is a famous binomial identity. A and B belongs to integers. I think this is also valid if they didn't belong to integer, and just n belongs to natural numbers. N belongs to natural numbers. So, but I was here in this step. So this part I can write it as n square minus 3 square into some k over n plus 3 into n minus 3 into n plus 3 k into n plus 3 cancelled out, and this part is what? This part is n minus 3 into some k, right? So this belongs to integer, and not even integer, this belongs to natural number. This belongs to natural number. Now let us go for one properties. Yes, this property we have already given in the theory session. This property, a natural number plus any x is n plus box x. Let us apply this. So this is also a natural number here. This is also a natural number, so we can apply that property. We're applying this property here. Applying this property here, we have n this part belongs to natural number. So we can apply that property of greatest integer function. Plus box of 3 to the power 200 over n plus 3. We have already proved at the very beginning that this n, which is nothing else but 10 to the power 100, is obviously greater than 3 to the power 200. So 10 to the power 100 plus 3 is greater than 3 to the power 200. N plus 3 greater than 3 to the power 200. So 3 to the power 200 divided by n plus 3 is less than 1, which implies that the value of this box will be equals to 0. So ultimately, the value of this expression, this large and ugly expression, reduces to the small expression which belongs to natural number we have proved. Now we need to find the unit digit. unit digit. Let's find it out. Nothing difficult. N is what? Some 10 to the power 20,000 minus 3 to the power 200 over 10 to the power 100 plus 3. Clearly the unit digit of this is 3. Denominator is 3 and it is also divisible. Let us find the unit digit of numerator. What will be the unit digit of numerator? 10 to the power 20,000. The unit digit of this will be what? Not even the unit digits. No. If I would say that the last 5 digits, this also is nothing else but simply 0, 0, 0. And what will be the unit digit of this part? Let's see. Quite easy. 9 to the power 100. 81 to the power 50. Now what will be the unit digit of 81? Since the unit digit of 81 is 1, whatever be the power, the unit digit of this expression will always be 1. Will always be 1. So unit digit of this is 1 and unit digit of this is 10. I can say 10. 0. Subtract this, the unit digit of numerator will be 9 and unit digit of denominator is 10 plus 3, which is 3. So the unit digit of this expression will be 9 divided by 3, because this is divisible. We have already proved this belongs to natural number. Is 3 and 3 is the correct answer. Such similar question we have already solved in this theory discussion. Let me show. Yes, similar question had already been solved in the theory session. This was quite easy for us.